Close your eyes for a moment. Feel the chair beneath you, the air on your skin, the steady rhythm of your breathing. You exist in 3 dimensions. You move left and right, forward and backward, up and down. Everything you have ever touched, smelled, tasted, seen, or loved exists within those 3 directions. Every mountain range, every ocean, every star you've ever squinted at on a dark night. All of it exists in a world of 3 spatial dimensions. And yet, something deeply strange has been bothering mathematicians and physicists for well over a century. Something that starts as an abstract idea, and the more you turn it over, the more it begins to feel like it might actually be true. The idea is this: those 3 dimensions you feel so certain about, the only 3 directions your body has ever moved through, may not be the whole story. The universe, according to some of the most carefully developed, rigorously tested, and mathematically precise theories we have ever constructed, may contain additional dimensions of space, directions that are real, physical, geometric features of the cosmos you inhabit, but directions that you have never moved through, never seen, never felt, and perhaps never will. Tonight, we're going to take that idea seriously, not as a metaphor, not as a spiritual notion, not as science fiction. We're going to explore extra dimensions as a genuine scientific and mathematical proposition, one that has roots reaching back into the 1800s, that has been pursued by some of the greatest minds in the history of physics, and that in the early 21st century sits at the center of our most ambitious attempts to understand why the universe works the way it does. This journey will take us from a quiet lecture hall in Göttingen, Germany in 1854, where a shy and sickly mathematician named Bernhard Riemann changed the way humanity thought about space, all the way to the Large Hadron Collider at CERN, where beams of protons smashed together at energies approaching the speed of light in the hope that something, a single particle, an anomalous trace of missing energy, a whisper of signal in a sea of noise, might betray the presence of a dimension we have never directly observed. We'll visit the office of an obscure German lecturer named Theodor Kaluza, who in 1919 sent a letter to Albert Einstein proposing an idea so strange and so beautiful that Einstein sat on it for 2 years before daring to publish it. We'll explore the curled and folded geometries of string theory, where 6 or 7 additional dimensions hide themselves in shapes smaller than anything physics can currently probe. And we'll sit with the profound philosophical question of what it even means for a dimension to exist, and what a being capable of perceiving those dimensions would experience when looking at our world. If you enjoy these deep dives into the mysteries of space and physics, a like or a subscribe helps this channel grow more than you know. And now, let's begin. Part 1. The edges of perception. Before we can talk about extra dimensions, we need to talk about dimensions themselves, what they actually are, and how we know we're in the ones we're in. A dimension, in the most fundamental geometric sense, is simply a direction, a degree of freedom, a way that something can be different from something else in pure spatial terms. When you describe the location of any object in our everyday world, you need exactly 3 numbers. You need a left-right coordinate, a forward-backward coordinate, an up-down coordinate. Give me those 3 numbers precisely, and I can find your cup of tea in an otherwise empty room. This is why we say we live in 3 spatial dimensions, not because someone declared it, but because three coordinates are exactly what it takes to uniquely describe every location in the space we inhabit. This might seem like the most obvious thing in the world, and for most of human history, it was never questioned. Euclid's geometry, codified around 300 BCE, described a world of points, lines, and planes. Aristotle, in his work On the Heavens, argued explicitly that space is three-dimensional, and that 3 is the only perfect number of dimensions because it is the only one that has a beginning, a middle, and an end. For more than 2,000 years, three-dimensionality was treated not as an empirical observation about the universe, but as a logical necessity and a priori truth about the nature of reality. Then the 19th century happened, and everything got stranger. The unsettling thing about our three-dimensional intuition is that it might actually be nothing more than the particular limitation of a three-dimensional nervous system. Think about how your perception works. Your eyes are two-dimensional sensors. Each retina is essentially a flat screen, a two-dimensional array of light-detecting cells. From these two flat screens, your brain reconstructs a three-dimensional model of the world around you, using subtle cues like shading, perspective, the slight difference between what each eye sees, the way objects overlap. You don't directly experience depth, you infer it. Your brain builds a three-dimensional model from two-dimensional input. This should give you pause. If your senses can reconstruct 3 dimensions from two-dimensional input, then ask yourself, would a three-dimensional creature necessarily be aware of a fourth spatial dimension if one existed? The answer, it turns out, is almost certainly no. If an additional dimension of space existed, but was rolled up very tightly, curled into a tiny loop much smaller than any particle of matter, then nothing about your sensory experience would differ from what it is right now. Your nerves would fire in exactly the same patterns. Your brain would build exactly the same three-dimensional picture of the world. The fourth dimension would be there, all around you, and you would have no idea. This isn't mysticism. It's the result of careful mathematical reasoning about what dimensions are and how they behave. And the story of how physicists came to take this reasoning seriously begins in one of the most beautiful and unexpected places in the history of science. The mind of a young German mathematician standing in front of an audience of his peers, proposing an idea that nobody present was quite prepared to understand. Part 2. A History of Dimensional Thinking. On June 10th, 1854, in the lecture hall of the University of Göttingen, a 27-year-old mathematician named Georg Friedrich Bernhard Riemann stood up and delivered what would become one of the most consequential lectures in the history of human thought. Its title, translated from the German, was On the Hypotheses Which Lie at the Foundations of Geometry. Riemann had prepared 3 possible talks for his habilitation, the European academic qualification required before a scholar could teach. By tradition, the examining committee was supposed to choose from among the 3. One of those committee members was the legendary Carl Friedrich Gauss, then in the last year of his life. Against Riemann's own expectations, Gauss chose the geometry lecture, the one Riemann considered least prepared. What followed electrified the old man. Riemann was shy and introverted, frail from what would eventually prove to be tuberculosis. He was not a performer, but what he proposed that day cracked open the very concept of space. He argued that there was nothing special nothing logically necessary about three dimensions. Space could have any number of dimensions: 2, 4, 10, 100, or infinitely many. More than that, he argued that space need not be flat in the Euclidean sense. It could be curved. It could have different curvatures at different points. And crucially, this curvature need not be embedded in any higher space in order to be defined. The curvature was intrinsic, a property of the space itself. To appreciate what Riemann was proposing, consider the surface of the Earth. The surface is two-dimensional. You can describe any location on it with two numbers, latitude and longitude, but the surface is curved. It bends back on itself. If you travel far enough in any direction, you return to where you started. That curvature is a real, measurable feature of the surface, even if you never leave it. You don't need to step off the Earth and look at it from outside to know it's curved. Riemann proved that the intrinsic geometry of a space, the way distances and angles behave within it, can reveal its curvature even to creatures who can't perceive the higher dimensional space in which it might be embedded. This was a conceptual revolution. Riemann had shown that space itself, not just the objects in space, but space as a geometric entity, could have properties. It could curve, it could bend, and there was no mathematical reason to restrict it to three dimensions. The lecture was delivered without a single equation. Gauss reportedly walked home afterward in unusual silence, visibly moved. He had long harbored private thoughts along similar lines, but Riemann had formalized them with a generality Gauss had never achieved. The lecture wasn't published until 1867, 2 years after Riemann's death, at the age of 39. By then, it would take mathematicians decades to fully absorb it, but it had quietly established the mathematical framework that 60 years later Albert Einstein would use to describe gravity as the curvature of four-dimensional space-time. While mathematicians were grappling with the abstract possibility of higher dimensional spaces, the general public had their own more popular encounter with the idea, delivered in a most unusual form. In 1884, an English schoolmaster and Anglican clergyman named Edwin Abbott Abbott published a slim novella under the pseudonym A. Square. Its title was Flatland, a romance of many dimensions. The book told the story of a two-dimensional world inhabited by geometric figures, triangles, squares, circles, pentagons, living their flat lives on an infinite plane. The narrator, a square named A Square, describes his world in loving detail. He has no concept of up or down. His universe has width and length, but no height. Objects are seen as lines. Social status is determined by the number of sides you possess. Then one day, a square is visited by a sphere from the three-dimensional world of Spaceland. To a square, the sphere appears as a circle that inexplicably grows and then shrinks. He's watching the sphere pass through his two-dimensional plane, which intersects it at different points along its surface. The sphere tries to explain depth to a square, and a square simply cannot grasp it. His senses, his intuition, and his entire framework of thought have been shaped by two dimensions. The third dimension is genuinely unimaginable to him, until the sphere simply picks him up and lifts him out of the plane, and a square suddenly sees his world from outside it, sees it whole, sees its depth in a way he never suspected. Abbott's book, initially overlooked, was rediscovered after Einstein published his general theory of relativity in 1915, and became enormously popular because readers suddenly understood that they were reading a parable about themselves. Just as a square was blind to the third dimension, we might be blind to a fourth. The analogy was obvious and deeply unsettling. Abbott's great fictional device, using a lower dimensional creature's confusion as a mirror for our own, remains one of the most effective tools anyone has ever found for making the idea of extra dimensions viscerally comprehensible. Around the same time Abbott was writing, the British mathematician Charles Howard Hinton was producing his own series of essays and books about the fourth dimension. Hinton coined the word tesseract in his 1888 book, A New Era of Thought, to describe the four-dimensional analog of a cube, and proposed a method for training oneself to visualize the fourth dimension using color-coded sets of cubes. He was convinced that with sufficient practice, the human mind could develop genuine four-dimensional intuition. His ideas were taken up enthusiastically by artists, spiritualists, and philosophers of the early 20th century. The fourth dimension became something of a cultural obsession in the years around 1900, referenced in the paintings of the Cubists, in the mystical writings of P.D. Uspensky, in the drawings of Marcel Duchamp. As Duchamp himself said, the fourth dimension became a thing you talked about without knowing what it meant. But underneath all the cultural ferment was something real. Riemann had shown that higher dimensional spaces were mathematically valid. Abbott had shown that creatures within a lower dimensional space couldn't directly perceive a higher one. And now Hinton was asking whether we might develop the tools to think about those spaces anyway. The stage was set for physics to take over. Part 3: The Mathematics of the Invisible. Before we follow physics into the quantum realm, it's worth pausing to understand what mathematics actually says about higher dimensional spaces, because the mathematical picture is both more rigorous and more strange than any intuitive illustration can fully capture. A point has 0 dimensions. Move that point a distance in one direction, and you trace out a line. 1 dimension. Move that line sideways a distance, and you trace out a square. 2 dimensions. Move that square perpendicular to its surface by a distance, and you trace out a cube. 3 dimensions. Now here is the question. What happens if you move that cube in a direction that is perpendicular to all 3 of its existing axes? You can't do it physically. You can't build it, but you can describe it mathematically, completely and consistently. The result is a tesseract, a 4-dimensional hypercube. A point has 1 vertex. A line segment has 2 vertices. A square has 4 vertices. A cube has 8 vertices. Following the pattern, each step doubles the count. A tesseract has 16 vertices. A line has 2 edges. A square has 4 edges. A cube has 12 edges. A tesseract has 32 edges. A square has 4 faces. A cube has 6 square faces. A tesseract has 24 square faces and 8 cubic cells. Every one of these properties can be derived by pure logical extension of the rules we use to describe lower dimensional shapes. The mathematics doesn't care that we can't see it. What we can do is project it. Think about how the shadow of a 3-dimensional cube looks on a flat surface. If you hold a wireframe cube up to a bright light and look at its shadow on the floor, you'll see a square inside a larger square with the corners connected by diagonal lines. That shadow is a 2-dimensional representation of a 3-dimensional object. You lose information in the projection. You can't see depth, but the structure is still recognizable, and certain properties are preserved. The same trick works for the tesseract. If you project a tesseract into three-dimensional space, what you get looks like a cube within a cube, with the corners of the inner cube connected to the corners of the outer cube by a set of additional edges. This nested, slightly eerie shape is what most people recognize when they see a tesseract depicted in art or animation. It's not the tesseract itself, it's the shadow of the tesseract, just as the cube within a square is the shadow of a cube. The Spanish surrealist artist Salvador Dalí understood this deeply. In his 1954 painting, Corpus Hypercubus, he depicted the crucified Christ suspended above the unfolded net of a tesseract. 8 cubes arranged in a three-dimensional cross. The four-dimensional object opened out into three-dimensional space, just as a cube can be unfolded into a flat cross of 6 squares. There are exactly 261 distinct ways to unfold a tesseract into 3 dimensions, just as there are 11 distinct ways to unfold a cube into 2 dimensions. Dalí's painting uses this mathematical idea as a spiritual metaphor, suggesting a transcendence of ordinary three-dimensional existence. Whether or not you find the metaphor apt, the underlying geometry is completely rigorous. The mathematician can go further than 4 dimensions with equal facility. 5-dimensional space, 10-dimensional space, 100-dimensional space. These are all perfectly well-defined objects in mathematics. The formal definition of an n-dimensional space is simply a set of points where each point is described by n coordinates, with appropriate rules about how distances and angles are measured. The mathematics doesn't break down or become contradictory. It simply becomes harder to visualize. By the time you reach 10 or 11 dimensions, any attempt to build physical intuition fails completely, and pure algebraic reasoning takes over. What Riemann understood in 1854 and what mathematicians have developed into an extraordinarily rich and detailed science in the century and a half since is that these higher dimensional spaces can have all sorts of different geometries. They can be flat, like infinite sheets of graph paper extended into higher dimensions. They can be curved positively, like the surface of a sphere generalized to higher dimensions. They can be curved negatively, like a saddle surface extended to more dimensions. They can be compact, rolling back on themselves like the surface of a sphere. Or they can extend to infinity. They can be smooth everywhere. Or they can have special points where the geometry becomes weird. The full landscape of possible higher dimensional geometries is one of the richest areas of pure mathematics, and it turns out to have deep and unexpected connections to the physics of our universe. One of the most remarkable facts in modern mathematics is that when you try to write down a consistent theory of quantum gravity that includes all the forces of nature, the mathematics seems to work best, sometimes only works, in a specific number of dimensions. This is not something anyone forced into the equations. It emerges from the internal logical structure of the theory. And the numbers that emerge? 10 dimensions in string theory, 11 dimensions in M theory, are precisely the kinds of higher dimensional spaces that Riemann's general framework was built to describe. Pure mathematical necessity, developed in the 19th century for entirely abstract reasons, turns out to match the requirements of the most ambitious physical theory ever attempted, This kind of unexpected convergence is one of the deepest and most haunting features of the relationship between mathematics and physics. Part 4. Einstein and the Fourth Dimension. Before physics could leap to 10 or 11 dimensions, it had to discover the fourth. And the story of how that happened is inseparable from the story of Albert Einstein and his two great theories of relativity. In 1905, Einstein published his special theory of relativity, and one of its most striking features was the way it treated space and time. In classical Newtonian physics, space and time were completely separate. Space was the static stage on which events unfolded, and time was the universal clock ticking away, identically for every observer everywhere. Einstein showed that this picture was wrong. Space and time are deeply, intimately connected. How much time passes between two events depends on how fast you're moving. Distances along the direction of motion shrink at high velocities. The very measurements that Newtonian physics treated as absolute and independent, lengths and durations, turned out to be relative, with different observers disagreeing about them. The mathematician Hermann Minkowski, who had actually been one of Einstein's professors in Zurich, realized in 1908 that the cleanest and most natural way to describe what Einstein had discovered was to treat space and time not as separate things, but as a single four-dimensional entity. He called it space-time. In Minkowski's space-time, every event, every point in space at a particular moment in time, is described by four coordinates. Three spatial coordinates giving where it happened, and one time coordinate giving when. And the geometry of this four-dimensional space automatically encodes the strange effects of special relativity. The way moving clocks run slow, the way moving rulers shrink, the way the order of events can depend on who's watching. This is the fourth dimension that most people have heard of, time as the fourth dimension. But it's important to be precise about what this means, because it's both more and less than it sounds. It doesn't mean that time is exactly like a spatial dimension. There's a crucial mathematical difference in the way time and space enter the geometry, encoded in what mathematicians call the signature of the metric. If all four dimensions were treated identically, you could rotate freely among them all. But in Minkowski spacetime, there's an asymmetry. The time dimension has a minus sign, where the spatial dimensions have plus signs. This is what makes cause and effect possible, what prevents you from traveling backward in time just by spinning around. Time is a dimension, but it's a different kind of dimension from space. Then, in 1915, Einstein went much further. In his general theory of relativity, he showed that gravity is not a force in the Newtonian sense at all. Gravity is the curvature of four-dimensional space-time caused by the presence of mass and energy. A massive object like the sun warps the geometry of the space-time around it, and what we perceive as the gravitational force pulling the Earth around the sun is actually just the Earth following the straightest possible path, a geodesic, through that curved four-dimensional geometry. Space and time bend. The geometry of the universe is dynamic, and the mathematical framework that made all of this describable was exactly the framework Riemann had developed in that lecture 60 years earlier. Think about what this means. Gravity, the force that holds planets in their orbits and keeps your feet on the ground, is not a force at all in the fundamental sense. It's a consequence of the shape of four-dimensional space-time, and the tool you need to describe it is differential geometry in 4 dimensions. Einstein didn't invent that tool. Riemann did in 1854, with no particular physical application in mind. The mathematician explored higher dimensional curved spaces out of pure intellectual curiosity, and 60 years later the physicist discovered that the universe uses one of those spaces as its stage. This set an extraordinary precedent. The mathematics of higher dimensional curved spaces, developed as abstract pure mathematics, turned out to describe physical reality. This precedent would prove enormously important when, just a few years after general relativity was published, someone asked the question, if gravity is geometry in 4 dimensions, could the other forces of nature also be geometry, but in 5? Part 5, Kaluza, Klein, and the first hidden dimension. The year is 1919. Theodor Kaluza is a lecturer in mathematics at the University of Königsberg, in what is now the Russian city of Kaliningrad. He is 34 years old, relatively unknown, and possessed of an idea so audacious that he has spent several months working up the nerve to send it to anyone. The idea is this: what if there is a 5th dimension of space, curled up into a tiny circle at every point in our 4-dimensional universe? And what if general relativity, Einstein's geometric theory of gravity, when written in 5 dimensions instead of 4, automatically and necessarily produces not only Einstein's equations for gravity, but also Maxwell's equations for electromagnetism? Kaluza's insight was startling in its economy. At the time, there were 2 known fundamental forces, gravity and electromagnetism. Gravity had just been beautifully explained as the curvature of 4-dimensional spacetime. Electromagnetism, the force responsible for light, magnetism, electric circuits, and chemical bonds, was described separately by Maxwell's equations, with no geometric interpretation whatsoever. These 2 great theories sat side by side, both extremely successful, with no apparent connection between them. What Kaluza showed was that if you simply extend Einstein's field equations to 5 dimensions, the mathematics does something remarkable. The 5-dimensional metric, the mathematical object that describes the geometry of spacetime, naturally breaks apart into a 4-dimensional metric. Einstein's gravity, a 4-dimensional vector field, Maxwell's electromagnetic field, and a scalar field. The electromagnetic field doesn't have to be put in by hand. It falls out automatically from the pure geometry of 5-dimensional space. Gravity and electromagnetism are unified. They are both aspects of the same higher dimensional gravitational theory. Einstein received Kaluza's letter in April of 1919 and was immediately struck by the idea. He wrote back describing it as enormously appealing at first glance. But he sat on the paper for 2 years, going back and forth, raising objections, reconsidering, before finally endorsing its publication in the Proceedings of the Prussian Academy of Sciences in 1921. There was, however, an obvious problem. If there is a 5th spatial dimension, why can't we detect it? Why does the world appear to have only 3 spatial dimensions? Kaluza himself handled this by imposing what he called the cylinder condition, a mathematical requirement that nothing in the physical theory actually depends on the 5th coordinate. This made the equations work beautifully, but it felt unsatisfying. It was essentially saying, there is a 5th dimension, but we're going to require that it plays no detectable role. Kaluza didn't explain why this should be so. The explanation came in 1926 from the Swedish physicist Oscar Klein. Klein proposed that the fifth dimension is not an extended infinite direction like the three spatial dimensions we're familiar with. Instead, it is compact, rolled up into a circle so tiny that it is completely imperceptible at the scales of energy and length that any experiment could probe. Imagine taking a two-dimensional sheet of paper, a flat, plain surface, and rolling it into a long, thin cylinder. From far away, the cylinder looks one-dimensional, just a line. It's only when you zoom in very close that you can see that each point on the line is actually a tiny circle, the cross-section of the tube. Klein proposed that something analogous happens at every point in space. Each point in our four-dimensional universe actually contains a tiny fifth dimension curled up into a circle of radius roughly equal to the Planck length, about 10 to the power of minus 33 centimeters, many orders of magnitude smaller than the nucleus of an atom. This explanation is now known as compactification. The extra dimension is there, but it's compact. You can move along it, but only in a loop, and the loop is so small that no particle of matter or probe of energy we have ever devised can detect the motion. The only way you'd notice the extra dimension was there is if you could accelerate particles to energies around 10 to the power of 19 giga-electron-volts, the Planck energy, which is about 1 trillion times more powerful than anything the Large Hadron Collider can achieve. At lower energies, the fifth dimension is simply invisible. Klein also discovered something beautiful: the quantization of electric charge. In classical physics, why electric charge comes in discrete multiples of the electron's charge is simply a fact that has to be taken as given. Klein showed that if charge arises from momentum in the compact fifth dimension, then the requirement that the wave function of a particle be single-valued around the circle automatically quantizes the allowed momenta, and therefore the allowed charges, in exact integer multiples. Charge is quantized because it is angular momentum in a compact direction. This was another profound unification. A deeply puzzling feature of electromagnetism had a simple geometric explanation in 5 dimensions. The Kaluza-Klein theory, as it came to be known, ultimately proved not to be the correct description of the world. It made some predictions about the masses and charges of elementary particles that didn't match what was observed, and it couldn't incorporate quantum mechanics in a natural way. Most physicists abandoned it by the 1930s, but the core idea that extra-compact spatial dimensions could unify forces and explain features of physics that would otherwise be mysterious never really died. It went underground, waiting for a framework powerful enough to resurrect it. That framework arrived in the 1970s and 1980s with string theory. Part 6, String Theory and the Architecture of Reality. To understand why string theory requires extra dimensions, we need to understand what string theory is trying to do. The 20th century produced 2 incomparably successful physical theories: quantum mechanics, which describes the behavior of matter and energy at the smallest scales, and general relativity, which describes gravity and the large-scale structure of space-time. Both theories are extraordinarily well tested. Both make predictions verified to extraordinary precision, and they are fundamentally incompatible with each other. When you try to apply the standard techniques of quantum mechanics to general relativity, when you try to quantize gravity, the mathematics produces answers that are infinite and meaningless. Every calculation you attempt fails. The two great theories of modern physics cannot be combined using the methods that work for every other force. String theory proposes a resolution. Instead of treating elementary particles as point-like, infinitesimal zero-dimensional objects, string theory proposes that every particle is actually an incredibly tiny one-dimensional string of energy. These strings are unimaginably small, roughly the Planck length in diameter, or around 10 to the power of minus 33 centimeters. They vibrate. Each different vibrational mode of a string corresponds to a different elementary particle. The electron, the quarks, the photon, the neutrino. All of these are not different fundamental objects. They are the same kind of string, vibrating in different patterns. And crucially, among the vibrational modes of a closed string is one that corresponds to the graviton, the quantum of the gravitational field. String theory automatically, necessarily, includes a quantum theory of gravity. The incompatibility between quantum mechanics and general relativity is resolved. But there's a price. When physicists worked out the mathematical consistency requirements for string theory, when they checked whether the theory was free of internal contradictions, they found that it only makes sense in a specific number of dimensions. Not 3, not 4, but 10. 9 spatial dimensions plus one time dimension. If you try to write the theory in fewer dimensions, certain mathematical pathologies appear. Anomalies, as physicists call them, that make the theory internally inconsistent. The requirement of 10 dimensions is not a choice anyone made. It's a mathematical necessity that emerges from the equations. The extra 6 spatial dimensions, beyond the 3 we observe, are handled exactly as Kaluza and Klein suggested. They are compact, curled up, but unlike Klein's single circle, the 6 compact dimensions in string theory can be wrapped up in extraordinarily complex geometries. The shapes they can form are called Calabi-Yau manifolds, named after the mathematician Eugenio Calabi, who conjectured their existence in 1954, and the mathematician Xingtung Yao, who proved their existence in 1977. A Calabi-Yau manifold is a 6-dimensional space with certain special symmetry properties. It preserves a property called supersymmetry in the 4-dimensional physics that remains after the other 6 dimensions are compactified. These manifolds are astonishing objects. They are not spheres or tori or any shape with a simple visual description. They are deeply folded, knotted, multidimensionally curved spaces with enormous topological complexity. Mathematicians have cataloged tens of thousands of distinct Calabi-Yau manifolds, and it's believed that the complete count could be staggeringly large. Hundreds of thousands, perhaps millions of distinct shapes. Each different Calabi-Yau shape gives a different pattern of compactification, and each different pattern gives different physics in the remaining 4 dimensions, different particle masses, different force strengths, different values for the constants of nature. The full set of possible physics that string theory can produce, the landscape of string vacua, may contain as many as 10 to the power of 500 distinct possibilities. This enormous landscape of possibilities is one of the most profound and controversial features of string theory, and we'll return to it later. In 1995, the physicist Edward Witten announced that the 5 different consistent versions of string theory that physicists had developed weren't actually 5 separate theories. They were all limits of a single, deeper theory, living in 11 dimensions, one more than string theory's 10. Witten called this 11-dimensional theory M-theory, and he chose the letter M deliberately without specifying what it stands for. Mystery, mother, membrane. All have been suggested. The 11th dimension in M-theory is different from the other 10. At low energies, it is a small spatial dimension, but at high energies, it becomes macroscopic, and the theory includes not just strings, but extended 2-dimensional objects called membranes or brains, and higher dimensional brains of various types. The low energy limit of M-theory, the limit in which the 11th dimension is small, is 11-dimensional supergravity, a theory that was known since the 1970s and that had been shown in 1978 by Werner Nahm to be the maximally consistent theory of supersymmetric gravity. Above 11 dimensions, no consistent supersymmetric theory of gravity exists. At exactly 11, it works. Below 11, string theory in 10 dimensions works. M-theory unifies the whole landscape. What string theory and M-theory suggest then is this: if these theories correctly describe physical reality, then the universe has either 10 or 11 dimensions of space-time. The 7 or 6 extra spatial dimensions beyond our observed 3 are compact, folded up in a Calabi-Yau geometry, so small that no current experiment can directly probe them. They nevertheless shape our world. The particular Calabi-Yau shape of the compact dimensions determines the spectrum of elementary particles we observe, the strengths of the forces, the masses of all the particles. Every property of the physical world we measure in particle accelerators could, in principle, be traced back to the specific geometry of dimensions we can never directly see. Part 7. Large extra dimensions and the hierarchy problem. String theory's extra dimensions in the standard picture are curled up at the Planck length, roughly 10 to the power of minus 33 centimeters. That's about 1 billion times smaller than the nucleus of a proton. No conceivable experiment could probe distances that small. The energy required would be roughly 1 trillion times greater than anything the Large Hadron Collider can generate. For all practical purposes, those extra dimensions are forever hidden. But in 1998, 3 physicists, Nima Arkani Hamid, Savas Dimopoulos, and Gia Dvali, proposed something radically different. They published a paper titled "The Hierarchy Problem and New Dimensions at a Millimeter," and it shook the theoretical physics community. Their proposal went by the initials ADD, and it suggested that the extra dimensions of space might not be Planck scale at all. They might be much, much larger. Large enough that experiments already in existence or soon to be built might detect them. To understand why this idea was so startling, you need to understand what physicists call the hierarchy problem. Among the 4 fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Gravity is peculiarly feeble. A small magnet can pull an iron nail off a table, overcoming the combined gravitational pull of the entire Earth. The electromagnetic force is roughly 10 to the power of 36 times stronger than gravity. The weak nuclear force is about 10 to the power of 25 times stronger. Why is gravity so absurdly weak compared to the other forces? this isn't just an aesthetic puzzle. It creates serious technical problems in quantum field theory because quantum corrections to the mass of the Higgs boson, the particle that gives other particles their mass, are naturally pushed up to enormous values by gravitational effects, requiring extraordinarily precise cancellations to keep the Higgs mass at the observed value. The hierarchy problem is the question of why these cancellations occur, or whether they really do. Arkani Hamed, Dimopoulos, and Diwali proposed a radical answer. What if gravity appears weak, not because it actually is weak, but because it is diluted by spreading into extra dimensions while the other forces cannot? In their model, all the standard model particles, quarks, electrons, photons, everything we observe, are confined to a four-dimensional surface called a brane, embedded in a higher dimensional bulk of space. Only the graviton, the quantum of gravity, is free to propagate through the entire bulk, including the extra dimensions. As a result, gravity's force lines spread out not just over three-dimensional space, but over the full volume of the higher dimensional space. By the time they reach macroscopic distances, gravity has been so diluted by spreading through the extra dimensions that it appears fantastically weak to us, even though its true strength at high energies is comparable to the other forces. What made the ADD model truly remarkable and made it experimentally testable was that the extra dimensions in this scenario could be surprisingly large. Depending on how many extra dimensions there are and how strong gravity really is at short distances, those dimensions could be as large as a fraction of a millimeter, not Planck scale small, not even atom scale small, potentially large enough to be probed by tabletop gravity experiments. And if they were, the nature of gravity itself would change at short distances. Instead of obeying Newton's inverse square law, the rule that gravitational force weakens as the square of the distance, gravity would strengthen faster at short ranges, following a steeper inverse power law depending on the number of extra dimensions. This was a genuinely testable prediction, and physicists immediately began testing it. The most elegant tests were carried out by the EOT Wash group at the University of Washington using exquisitely sensitive torsion balance experiments. A torsion balance works by hanging a delicate pendulum from a thin fiber and measuring the tiny twists in the fiber caused by gravitational forces between test masses. The EOT Wash experiments tested gravity at distances from millimeters down to about 55 micrometers, less than the width of a human hair, and found no deviation from Newton's inverse square law. In 2020, the team published results showing the inverse square law holds down to at least 52 micrometers. The result constrained the size of a single large extra dimension to be no more than about 44 micrometers. Two extra dimensions of equal size are constrained to be smaller than about 130 micrometers. Large extra dimensions at the millimeter scale for two extra dimensions were ruled out. Just 1 year after ADD, in 1999, physicists Lisa Randall and Raman Sundram proposed an even more elegant solution to the hierarchy problem, one that didn't require large extra dimensions, but instead used a warped extra dimension to generate an exponential hierarchy of scales. Their model, known as the Randall-Sundram or RS model, posits a single extra spatial dimension shaped by a specific kind of curvature, an anti-de Sitter geometry with negative cosmological constant. 2. Four-dimensional brains sit at the boundaries of this five-dimensional bulk. On one brain, called the Planck brain or gravity brain, gravity is strong. On the other brain, called the TeV brain or weak brain, where we live, gravity appears weak. The crucial point is that this exponential suppression of gravity on our brain is a natural consequence of the geometry. The graviton's probability function, the quantum mechanical amplitude for finding a graviton at a given location, is strongly peaked at the Planck brain and drops exponentially as you move toward the TeV brain. This means the graviton interacts very weakly with particles on our brain, not because gravity is intrinsically weak, but because the graviton is exponentially unlikely to be found where we are. The warped geometry automatically generates the enormous hierarchy between the Planck scale and the electroweak scale, 16 orders of magnitude of suppression without any fine-tuning of parameters. The Randall-Sundrum model made specific predictions for particle colliders. If there is a warped extra dimension, then there should exist a tower of massive particles called Kaluza-Klein gravitons, excited vibrational modes of the graviton that carry the imprint of the extra dimension's quantized geometry. Each Kaluza-Klein mode would have a specific calculable mass, and each would decay into pairs of particles in predictable ways. At the Large Hadron Collider, physicists searched for these resonances in dilepton and diphoton channels. As of the most recent searches, no Kaluza-Klein gravitons have been found, and their masses are constrained to be above roughly 4 tera-electron volts. 4 times the mass of a proton multiplied by 1,000,000,000,000. No signal has appeared, but the absence of a signal isn't the end of the story. It constrains the parameter space, narrows the possibilities, and in many cases definitively rules out certain models. The search continues. Part 8. Searching for the invisible. Experiments and evidence. One of the most important questions in experimental physics is whether we can ever actually detect an extra dimension. The theoretical proposals are elegant and mathematically compelling, but science lives and dies by experiment. What are the concrete signatures that extra dimensions would leave in our physical world, and what have experiments found? The Large Hadron Collider at CERN. The 17-mile circular tunnel beneath the French-Swiss border in which protons smash together at energies approaching the speed of light is one of the most powerful tools humanity has ever built for probing the structure of matter. It accelerates protons to 99.9999991% of the speed of light, and collides them at a combined energy of up to 13.6 trillion electron volts. In the debris of these collisions, physicists search for evidence of particles and interactions that the standard model doesn't predict. For extra dimensions, the LHC offers several possible signatures. The most direct is the production of Kaluza-Klein gravitons, the massive spin-2 particles predicted by both the large extra dimensions scenario and the Randall-Sundrum model. If a KK graviton is produced in a collision, it would decay into pairs of leptons or photons with a specific invariant mass, creating a resonance peak in the mass distribution. Physicists at both the ATLAS and CMS experiments at the LHC have searched for these peaks across many years of data taking. The analyses have been extensive and extraordinarily careful. No resonance has been found. Current limits place the mass of the lightest Kaluza Klein graviton above several tera-electron volts, depending on the specific model parameters. A second signature is the production of gravitons that escape into extra dimensions. If extra dimensions exist and gravitons can propagate into them, then some collisions should produce a graviton that disappears into the higher dimensional bulk, carrying energy away. From the perspective of our detectors, which can only see particles that stay in our four-dimensional space, this would look like a collision where energy seems to go missing, violating conservation laws from our perspective. These are called monojet or monophoton events. Collisions where a single energetic jet of particles recoils against apparently nothing because its partner, the graviton, has escaped into extra dimensions. The LHC has searched for these events with great care. The absence of an excess in these searches has placed stringent lower limits on the fundamental scale of quantum gravity in the ADD model. Beyond collider experiments, there are other remarkable ways to test for extra dimensions. One of the most unexpected came in August 2017, when the LIGO and Virgo gravitational wave detectors observed the collision of two neutron stars. The event, known as GW170817. Crucially, this merger was also observed in light, as a short gamma-ray burst detected 1.7 seconds after the gravitational wave signal. This near-simultaneous arrival of gravitational and electromagnetic signals from the same astrophysical event was profoundly important. In certain brain-world models where gravity can propagate through extra dimensions, gravitational waves and electromagnetic waves would follow different paths between 2 points on a brain, potentially arriving at different times. The near simultaneity of GW170817 and its electromagnetic counterpart placed new and independent constraints on the geometry of possible extra dimensions, ruling out or significantly constraining some brain-world scenarios. Astrophysics provides additional constraints. In 1987, a supernova explosion in the Large Magellanic Cloud, designated SN1987A, provided a burst of neutrinos detected on Earth. In the ADD model of large extra dimensions, the hot, dense core of an exploding star should produce Kaluza Klein gravitons copiously, carrying energy away into extra dimensions and cooling the supernova core faster than expected. The fact that SN1987A produced a neutrino burst consistent with standard supernova models places constraints on the scale of extra dimensions for two additional dimensions. The fundamental Planck scale must be above roughly 27 tera-electron volts for this scenario. Then in 2022, an entirely new approach emerged from the theoretical frontier. Harvard physicist Kumrun Vafa, working with colleagues Miguel Montero and Irene Valenzuela, developed what they called the dark dimension scenario. This proposal connects the observed smallness of dark energy, the mysterious energy density of the vacuum, responsible for the accelerating expansion of the universe, to the existence of a single extra dimension at the micron scale. The argument is elegant and draws on a set of theoretical conjectures about what kinds of physics are consistent with a complete quantum theory of gravity, known as the swampland program. The reasoning goes roughly like this. The cosmological constant, dark energy, has a value that in natural units is the smallest dimensionless number ever measured in physics, about 10 to the power of minus 122 in Planck units. Such an extreme smallness, according to the swampland conjectures, implies the existence of a tower of very light particles. The lightest consistent possibility is a tower of Kaluza-Klein graviton modes arising from a single extra dimension whose size is roughly 1 micron, about 1,000th of a millimeter. This dark dimension proposal is remarkable for several reasons. First, it unifies two of the deepest mysteries in modern physics: the origin of dark energy and the origin of dark matter. In the model, dark matter is composed of the massive Kaluza-Klein gravitons that inhabit the micron scale extra dimension. These gravitons are weakly interacting, gravitationally coupled particles, perfectly plausible dark matter candidates that don't require any new physics beyond what string theory already predicts. Second, and more excitingly, the proposal is actually testable. If there is a single extra dimension at the micron scale, then gravity should deviate from the standard inverse square law at distances of roughly 1 to 30 microns. This is precisely the scale that next-generation tabletop gravity experiments are designed to probe. Experiments are currently being improved to push gravity tests below the 10-micron scale. If the dark dimension is there, we might find it within this decade. The current state of experimental knowledge about extra dimensions is essentially this: we have not found them, but we have constrained them in increasingly powerful ways. Large extra dimensions at scales of a millimeter or more are ruled out for 2 or more extra dimensions. Kaluza-Klein gravitons below masses of several tera-electron volts have been excluded. Brain-world models that would cause detectable time delays in gravitational versus electromagnetic signals have been constrained. And yet the theoretical motivation for extra dimensions, from string theory, from the hierarchy problem, from the dark dimension scenario, remains strong. The null results so far have narrowed the search, but they haven't closed it. Part 9: Philosophical and Perceptual Frontiers. All of this mathematics and experimentation sits on top of a set of philosophical questions, so deep and strange that they can be dizzying to contemplate seriously. What does it even mean for a dimension to exist? Could we ever directly perceive one? And if the universe has more dimensions than we can sense, what does that imply about the nature of our experience of reality? Let's start with the perceptual question, because it's the most viscerally unsettling. Imagine you are a square, Abbott's hero from Flatland. You live in 2 dimensions. You have never experienced depth, never moved up or down, never conceived of anything other than length and width. Now a sphere from 3-dimensional space enters your world. From your perspective, the sphere doesn't appear as a 3-dimensional object. It appears as a mysterious circle that materializes, expands, then shrinks and vanishes. The intersection of the sphere's volume with your 2-dimensional plane, which the sphere is passing through. The sphere tries to explain depth to you. You can't grasp it because you have no sensory apparatus for depth, no neural machinery that has ever processed depth information, no concepts that refer to depth. The sphere is gesturing at something real, something present, something close, and you simply cannot access it. Now consider the analogy to our situation. We are 3-dimensional beings. Our bodies, our brains, our sensory organs have all been shaped by evolution to process information from a 3-dimensional world. If there is a 4th spatial dimension, our sense organs don't measure it. Our nervous systems don't model it. Our brains don't simulate it. We would be like a square trying to grasp depth. But, and this is the important point, unlike a square, we have mathematics. We can describe 4-dimensional or 10-dimensional geometry with complete precision. We can work out all its properties. We can make physical predictions. We just can't see it. What would a 4-dimensional being be able to do that a 3-dimensional being cannot? The answer follows directly from the pattern established by dimensional analogy. A 2-dimensional being can see the inside of a 3-dimensional box only if the box is opened. A 3-dimensional being can see the inside of a 3-dimensional box from outside just by looking in. Similarly, a 4-dimensional being would be able to see the inside of any 3-dimensional object simultaneously. The inside of a closed vault, the interior of a living body, without cutting it open, because from the 4-dimensional vantage point, the interior of any 3-dimensional object is exposed in the direction perpendicular to 3-dimensional space. A surgeon from a 4-dimensional world could perform surgery without making an incision. A thief could reach into a locked safe without opening it. The locked room is only locked from a 3-dimensional perspective. More specifically, consider what a 4-dimensional being would see when it looked at you. Your internal organs would be visible. Every atom of your body, not just the surface, would be simultaneously accessible. Your skin would be no barrier. The concept of inside and outside would not apply to your body in the way it applies to a 2-dimensional creature's area inside a line. There is also the strange question of chirality. In 3-dimensional space, your left hand and your right hand are mirror images of each other, but they cannot be superimposed by any rotation. They are genuinely different from each other. In 4-dimensional space, however, you can rotate a 3-dimensional object through the 4th dimension and flip it into its mirror image. In exactly the same way that a 2-dimensional letter R can be flipped into a reversed R by lifting it out of the plane, rotating it in 3-dimensional space, and setting it back down. A 4-dimensional being could pick up your left hand, flip it through the 4th dimension, and set it back down as a right hand. The biochemistry of your body would immediately be disrupted because biological molecules are chiral. They only fit together in specific left-right orientations. A 4-dimensional visitor who handed you a sugar molecule rotated through the 4th dimension would be giving you something your metabolism couldn't process. The philosophical implications of extra dimensions go deeper than perception and extend into questions about the nature of causality, determinism, and consciousness. Some thinkers in the late 19th and early 20th centuries argued that a 4th spatial dimension could account for the apparent freedom of the will, that the causal chains of 3-dimensional physics might be open in a higher dimension, allowing choices that from a 3-dimensional perspective appear uncaused. This argument is now generally considered confused. Extra spatial dimensions don't break determinism in any obvious way, but it illustrates how powerfully the idea of extra dimensions has been seized upon as a way of thinking about the limitations of our ordinary physical worldview. More recently, the concept of extra dimensions has found its way into discussions about the simulation hypothesis, the idea that the physical universe might be a computation running in some larger substrate. If our universe is embedded in a higher dimensional space, then the laws that govern our universe from within might look like constraints imposed by the structure of that higher dimensional space from without. The rules of physics might be, in some sense, the geometry of a higher dimensional room. This is not a scientific claim. The simulation hypothesis is currently unfalsifiable, but the analogy between Kaluza-Klein compactification and a room of extra-dimensional space that generates apparent three-dimensional physics is suggestive in a way that makes some philosophers uncomfortable and others genuinely excited. There is also a deeper question about whether our concept of dimension is fundamental to reality, or whether it is itself something that emerges from a more basic structure. In string theory and M theory, space itself is not a fundamental entity. Space-time emerges from the behavior of strings and branes. The number of dimensions we observe might not be a given feature of reality, but a consequence of the particular way in which the more fundamental underlying theory manifests at low energies. Some research programs like loop quantum gravity and causal dynamical triangulations suggest that smooth space-time, and with it, a definite number of dimensions, might only emerge at macroscopic scales from a more granular, discrete underlying structure in which the concept of dimension doesn't straightforwardly apply. If that's true, then the question of how many spatial dimensions exist might not have a clean answer at the most fundamental level. It might be an approximate, emergent description, the way temperature is an emergent description of the average kinetic energy of molecules. These are among the deepest open questions in both physics and philosophy, and the answers, if they come, may require the same kind of conceptual revolution that Riemann's lecture initiated in 1854. A revolution that requires us to give up something that feels as certain as the three-dimensionality of space. Part 10. The Future of Dimensional Physics. We are living through an extraordinary moment in the history of this question. The experimental tools have never been more powerful. The theoretical ideas have never been more developed. And the prospect of genuine experimental contact with the question of extra dimensions, something that would have seemed fantastical even 30 years ago, is now genuinely within reach. At the forefront of near-term experimental possibilities is the dark dimension proposal. If Kumrun Vafa and his colleagues are right, there is a single extra spatial dimension at the micron scale, and its effects should manifest as a deviation from Newton's inverse square law of gravity at distances of a few microns. The current best measurements test gravity down to about 52 micrometers. New experiments are being developed that will probe gravitational behavior at distances of 10 micrometers or less. These are extraordinarily delicate measurements. At these scales, the gravitational force between test masses is barely distinguishable from electromagnetic and van der Waals forces between the same surfaces, and enormous care is required to shield against these competing effects. But several groups, including the Iut-Wash group at the University of Washington and teams in China and Europe, are actively developing the next generation of short-range gravity experiments. Within this decade, we should have definitive tests of gravity down to the few micron scale. If a deviation from the inverse square law is found, the implications would be revolutionary. It would be the first direct experimental evidence that the universe has more than 3 spatial dimensions. It would transform string theory and M theory from mathematically elegant but experimentally untested proposals into falsified or confirmed physical theories. It would almost certainly provide new insights into the nature of dark matter, dark energy, and the hierarchy problem. And it would force a complete rethinking of our understanding of gravity at short distances, with profound implications for our understanding of what happens inside black holes and at the beginning of the universe. The high luminosity LHC, currently being upgraded and expected to begin operation around 2029, will collect roughly 10 times more data than the current LHC run. This huge increase in data will extend the sensitivity of searches for Kaluza-Klein gravitons and missing energy signatures into mass ranges well above current limits. If extra dimensions are relevant to the electroweak scale, if they address the hierarchy problem, then some signature might appear as the dataset grows. Similarly, the proposed Future Circular Collider, a 100-kilometer tunnel being seriously discussed for construction at CERN, would operate at collision energies 7 times greater than the LHC and could probe mass scales up to tens of tera-electron volts. If Kaluza-Klein gravitons exist in the few TV mass range, such a machine would find them. Gravitational wave astronomy is opening another window. The LISA mission, the Laser Interferometer Space Antenna, is a space-based gravitational wave detector approved by the European Space Agency, with a planned launch around 2035. LISA will observe gravitational waves from sources at far greater distances than LIGO and Virgo, using a triangle of spacecraft separated by 2.5 million kilometers. Among its capabilities is the detection of gravitational waves from the merging of supermassive black holes in the centers of distant galaxies. These events are so luminous in gravitational waves that they can be detected across cosmological distances. If extra dimensions exist, the propagation of gravitational waves over these cosmological distances should show imprints, subtle modifications to the wave's amplitude and phase, that could distinguish higher dimensional gravity from standard 4-dimensional general relativity. Cosmological surveys also offer indirect probes. The large-scale structure of the universe, the distribution of galaxies and galaxy clusters, is sensitive to the nature of gravity on cosmological scales. If gravity behaves differently from general relativity at any scale because of extra dimensions, this difference would be imprinted in the growth of structure over cosmic time. Next-generation surveys like the Euclid mission, the Vera Rubin Observatory, and the Square Kilometer Array are mapping the universe with unprecedented precision. Their data will allow much tighter constraints on any scale-dependent modifications to gravity, including those predicted by certain extra-dimensional models. On the theoretical side, the Swampland program, the effort to understand which theories of physics are consistent with quantum gravity, has become one of the most active areas of research in string theory. The dark dimension proposal emerged from Swampland considerations. Other Swampland conjectures make predictions about the spectrum of fundamental particles, the range of possible coupling constants, and the dynamics of the early universe. These conjectures are not yet proven theorems. They are well-motivated guesses based on patterns observed in string theory, but several of them have been corroborated by independent calculations. If the Swampland program matures into a rigorous set of principles, it could provide a much sharper set of predictions about extra dimensions and their observable consequences. There is also the ongoing mathematical work on Calabi-Yau manifolds and string compactifications. Physicists and mathematicians are developing new tools, computational geometry, machine learning applied to the vast landscape of string vacua, algebraic geometry of compactification spaces that are beginning to make the enormous landscape of possible string theories more navigable. The hope is that some principle, some selection rule, some dynamical mechanism might single out a particular compactification as the one that describes our universe. Finding that compactification would mean finding the explicit geometry of the hidden dimensions. It would mean reading off the number and type of elementary particles from the topology of a six-dimensional Calabi-Yau space. It would mean understanding every measured constant of nature as a geometric property of a space so small that nothing we can build will ever directly probe it. The deepest possibility is that one of these theoretical or experimental threads leads to a genuine discovery, a signal in a detector, a deviation in a measurement, a convergence of theoretical reasoning that forces us to accept that the universe has more spatial dimensions than we can directly sense. That moment, if it comes, will be one of the most profound in the history of science, more profound in some ways than the discovery of quantum mechanics, more profound than the discovery of relativity, because it will require not just a revision of our mathematical framework, but a revision of our deepest intuitive sense of what space is, the feeling of solidity that we take for granted, the sense that up and down, left and right, forward and backward, exhaust the possible directions of the universe, will be revealed as a limitation of our nervous systems, not a fundamental feature of reality. And yet, in a strange way, that limitation is also beautiful. We are three-dimensional creatures who have built, through mathematics and experiment, a map of a world that contains more than three dimensions. We have extended our perception not with new senses, but with reasoning. We have looked at the numbers that describe gravity, the equations that unify forces, the constraints that quantum mechanics places on space-time geometry, and we have inferred from those abstract structures the likely presence of directions we can never walk. We have done, in effect, what Riemann did standing in that lecture hall in Göttingen in 1854, taken the cold mathematics of geometry and used it to see beyond what the eye can show us. Whether or not extra dimensions are ultimately confirmed, the attempt itself is one of the most remarkable things that minds shaped by three-dimensional existence have ever achieved. The faint possibility of a fourth direction, a fifth, a sixth, curled up, hidden, impossibly small, but mathematically real, is out there, in the geometry of a tiny vibrating string, in the compactified volume of a Calabi-Yau manifold, in the warped curvature between two cosmic brains, in the micron scale wiggle of gravity that next generation experiments are beginning to search for, in the equations of M-theory hovering at 11 dimensions with their strange perfection, somewhere in the mathematics of how forces unify and particles acquire their masses. The hints of those hidden directions accumulate, quietly patient, waiting to be found. Tonight, as you drift towards sleep, carry that strangeness with you. The room around you, with its familiar three directions, may not be all there is. The space you move through may be richer than it appears. The universe may have architecture that your body cannot feel, but your mind, stretched by mathematics and experiment and The long tradition of human curiosity has begun to reach toward. We have barely begun to look, and the looking itself is extraordinary. If this journey through the hidden geometry of the universe resonated with you, a like or a subscribe helps more than you know. It's what allows this channel to keep exploring the universe's deepest mysteries, one long, careful, quiet conversation at a time. Sleep well and dream in all the dimensions you can.